Hi, everybody. Welcome to the final video for Unit 5, right? So we'll be ending our torque and rotational dynamics questions or unit here in topic 5.6, which is Newton's second law of rotation, okay? So this is, again, like if we look at a progression, first law, no change in angular velocity, right? So no angular acceleration. Second law, now we're going to have an angular acceleration. So angular velocity changes when you have a net torque exerted on a system or an object, okay? The rate at which the angular velocity of the rigid system changes is directly proportional to the net torque on the rigid system and is in the same direction. So we extend out in the last video, we said the sum of the torques is equal to 0. In this video, the sum of the torques is going to be I times alpha. Again, Newton's second law said that the sum of the forces is m times a. Remember, I is the rotational equivalent of m. Alpha is the rotational equivalent of mass, right? Or sorry, acceleration. And I, moment of inertia, is the rotational equivalent, or sorry, torque. It should be sum of the taus, not i's. So the sum of the taus is equivalent to force. So the angular acceleration of a rigid system is inversely proportional to the rotational inertia of the system. So again, so these two, I is directly proportional to tau, I is inversely proportional to 1 over a. So those are our two main relationships. And to fully describe a rotating system, the linear and rotational analysis may need to be performed independently. So what you have to do is you create a rigid body diagram, right, where you show all the forces acting in the point of application. And then you do like what we did in the previous example, we split it up. X, sum of the forces in the X, sum of the forces in the Y, sum of the torques, okay? And the other main equation that you do have to remember for this particular area is the relationship between translational acceleration and rotational acceleration, okay? Because you may need to figure out what alpha is and then solve for this translational acceleration. Or you get everything in terms of one thing and then substitute it in, right? Because it comes with systems of equation. So if I'm looking at a rigid body diagram for my pulley here, I do have the weight down. I do have this force up here. But something to note is that these forces do not cause rotation. So because they're going to be at the axis of rotation. So now I have tension on one side, tension on the other side. Not F2, but tension. So this would be a T. Okay. And then typically you have something like a mass down here. So they would bring in Atwood machines. And so you would have to do free body diagrams for the blocks that are hanging off as well as the pulley. And so the blocks would be forces. The pulley would be rotation. Okay. But T1, T2 come from the pulley or come from the blocks that are hanging off of it. All right. So let's see this in action. Okay, so here we have we're pulling with a downward force that passes over a disc-shaped pulley. And that's important because the disc shape tells us that the disc is 1/2 mr squared. So the I sorry, I kind of wrote it really tiny off here to the side. All right, so I'll write it over here. So the moment of inertia for disk is 1/2 mr squared. So you can determine that right now, or you can do some algebra, okay? So if I'm looking at one side, if I split this into two, I have the sum of the forces on the left is equal to 0, right? Because I'm going to pull with a constant velocity, okay? So that means that the pull force is equal to the only thing over there, right? The net force. Oh, sorry. So we have Sum of the forces on the left is equal to 0. So I have the pull minus the tension is equal to 0. So pull equals tension. So the tension on the left side is easy, 28 newtons. Okay. So I'm done with the left-hand side where the hand is. Now I look at the right-hand side. I draw a free body diagram. I have mass down. I have tension up. And so this side will be accelerated in an upward direction. So T2 minus mg equals ma. And so T2 is going to be mg plus ma. Now I can pull out the m, but maybe I have something with a involved later that I can substitute in for. All right, and now we look at the pulley. So I have T2 down, I have T1 down, and I know it's going to rotate in this manner, right? So my alpha is going to be rotating in a counterclockwise manner, so it's positive, which is important. So I'd have the torque caused by 1 minus the torque caused by 2 equals I alpha. Again, sum of the i's, or sum of the torques, keep screwing that up, sum of the torques is equal to I times alpha. But remember, alpha will be translational over radius. Okay, and so I can substitute that in. Let's just substitute in all of our equations so we can kind of move forward with the problem. I erased half of it. So this is R1 T1 minus R2 T2 equals I times A over R. But the good thing is R1, R2, and R are all the same thing. So I can cancel all these out. So I end up with T1 minus T2 equals I times alpha. Okay. Now I can substitute in here if I want. Oh, sorry, I times A, not alpha. So I times A. I can substitute in here if I want. It probably makes it a little bit easier. Okay. But the thing is, I need A, right, to go away. I'm looking for T2 because I already have T1 or T left, right? I already have that. Now I'm looking for T2. So if I substitute in I now, so T1 minus T2 equals 1/2 mr squared A. Okay. Oh, hold on. I kind of goofed a little bit. For me to make this calculate these here, oh, sorry. So I need to go back to this point and kind of redo this algebra a little bit. Okay, for some reason I can't erase. There we go. Okay, so I have RT1 minus RT2 equals, now I'm going to substitute in the 1/2 mr squared here, and that's going to be A over R. So this cancels this one, and then this R, what's left over, cancels these R's. So I have T1 minus T2 equals 1/2 MA. Okay. Now, where we go from here is up to you on how you want to solve this. Okay. I can figure out, notice that MA is T2 minus mg. I can substitute that over here. So T1 minus T2 equals 1/2 mg, T2 minus MA. Okay, but note that M is the block, okay, not the, in fact, we can't make that substitution because it's the block. Okay, so if I want to solve this for A, I would get 2 T1 minus T2 over mass of the pulley, right? And so I can now take this, again, it's like a lot of algebra here, so I'm going to substitute in over there. And so you end up with T2 equals, and you could put in numbers now if we want to do that, kind of like simplify this even further. In fact, let's do that. So this becomes 2 times, right, divided by 1.2. So whatever 56 divided by 1.2 is. So that becomes, again, like just try to simplify as much as you can. We'll call that 47 minus, let's see, A, so we're going to multiply that by 2, divide by M, so then becomes 2t, so if I do 2 divided by 1.2, it gives me 1.7. Sorry. Sorry for all this confusion. I'm opening up apps and getting crazy. I do apologize for that. Stop this. All right. Sorry. So I get 1.7 T2. And now I can substitute that in for A. So I get mg plus this equals T2. Add T2 to both sides. So I get 2.7 T2 equals mg. So 6.7 plus 47. Okay, so 6.7 plus 47. So this is 2.7 equals 53.7. And then I divide 2.7 T2. And I do 53.7 divided by 2.7. And I get an answer of approximately 20. I have a feeling that it's not. I think because of rounding, right, we're somewhere, and I apologize for going crazy, but I'm not going to try to fix it. So our answer is approximately 20 newtons. I think the answer is more around 18 something because of, I solved it a little bit different when I did it before. If there's a mistake, I'll put it into the comment section to say, hey, I made a mistake. All right, so that's the end of Unit 5. In Unit 6, we'll continue talking about rotation, but we're going to focus on conservation quantities like momentum and energy.